that was really poor protocol, and it wasn't it was really funny.
Okay, we're gonna get started. We're just gonna be wrapping up chapter 5 real quickly. We've got a couple of just nails that we're gonna put in the coffin, and after that, next week we're gonna start chapter number 6. So, what's that? I'll probably get through chapter number 6, and then after moving through chapter number 6, that's probably when I'll give you that second exam. And so it'll probably take me through next week to finish up chapter 6. Just double check and make sure there's nothing in chapter 7 that I care about. Yeah, so we'll test on material up through chapter 6, not next week, but the following week. So that means exam number 2 is going to be the week after this, or week after next, right? We'll lecture next week. I'll probably have it on Thursday, so we'll have it late in the week. So I'll come in on Tuesday of that week and do some lecturing, and then on Thursday we'll do chapters. We'll do the exam. Okay, so last time we introduced this equation. dg is equal to v dp minus s dt, and then we graphed the potentials of different phases on graphs together, the chemical potentials, and we saw how this relationship leads to the I guess differential stability of one phase to another with changes in pressure and temperature. So should I put those graphs up? You weren't here for them. Do you want to take a look at them real quick? All right, let me just put those guys on the screen. Here. I like those.
Did you fix the graphs?
No, I didn't fix that one. You'll just have to watch the lecture video and remember what I said. Oh, there was just one thing that I mislabeled. Okay. All right. So here's the first set of graphs that we were looking at. So we had the slopes of the chemical potential that gives free energy. It's also referred to as the chemical potential. So if you hear that vocabulary, just remember that they're the same thing: chemical potential and gives free energy. With respect to pressure, and over here we said that the multiplier in front of the differential change in pressure is the volume, and so the slope of the graph of chemical potential is going to be proportional to the volumes. And so if we're considering just the gas, solid, and liquid phases of one substance, the gas phase chemical potential will increase more highly with pressure. And if the liquid is larger in volume than the solid, then the liquid will be next in line, and the solid will have the smallest. And so that resulted in low pressures favoring the gas phase, because the gas phase dips down to lower chemical potential at low pressure, and high pressures favoring the solid phase. And we kind of said that what that means is that the higher pressure that you have on something, you're kind of forcing it down into the more condensed phase. And if the solid phase is the most condensed phase, it's going to be favored at high pressures. Obviously, the gas phase is the least condensed phase, and so it will be the least favored at high pressures, and therefore it's going to be the most favored at the low pressures. We looked at this guy. We said that for water, the slopes of the liquid and the solid are inverse. See over here, the liquid slope is greater than the solid, but over here, the solid slope is greater than the liquid. And so this means that at high pressures, the liquid phase is going to be the most stable state. So that was the pressure relationship. And we took a look at these graphs for the temperature relationship. relationships. The multiplier in front of the temperature differential over there in our Gibbs free energy expression, or TG expression, is the molar entropy of the substance. And so because in general the entropy of a solid is less than the entropy of a liquid is less than the entropy of a gas, we have the relative slopes. The gas slope is the largest slope. There's a negative sign in front of it, and so it has a large negative slope for Gibbs free energy versus temperature. Solid or liquid phase is next in line, so its slope is the next greatest in magnitude, although it's slightly smaller. And the solid phase has the lowest entropy, and so it's got the least negative slope, right? And again, whichever one goes to the lowest chemical potential is going to be the one that's favored at that particular temperature. And so you see that because the gas phase has because the gas has the largest negative slope, at high temperature the gas is going to be favored. We know this. You stick a bunch of energy into a substance, and increasing its temperature, you're going to drive it off into the gas phase, right? And for low temperatures, because the solid has the least entropy, the solid ends up being favored at low temperatures, right? And we define those points of intersection of the graphs as being places where the two substances are at equal chemical potentials. And you'll see here that in these graphs, we have only intersection of two curves at a time. And so just by looking at one of those graphs, you might be tempted to think that it's never true that the solid, the liquid, and the gas phases are in equilibrium. But we kind of know from general chemistry that that happens, right? There is a condition in which solid, liquid, and gas phases can be at equilibrium, and that's called the triple point, right? And so what I want you to remember about that is that when we took this, we graphed this kind of general description of Gibbs energy versus temperature, we were holding it at one particular pressure, right? And we kind of showed over here that if we regraphed the lines at a new pressure right on top, that there would be predicted changes, and that from those changes we could predict the elevation of the boiling point, the depression of the freezing point, things like this with changes in pressure. Another thing that I want you to be able to do is to look at that graph and understand that if we choose just the right pressure, we can bring all of these lines to a point where the chemical potentials of all phases are equal, right? So we showed you that you've taken this at one pressure, and then when you change it to a new pressure, the curves all shift. And just understand that there's one particular pressure at which you can bring all of those curves together into one particular value of temperature and pressure at which the chemical potentials are equal for all of those substances. You guys remember this stuff? You'll have to watch the YouTube. Did you already watch it? So, a couple of things we want to talk about. One, we're gonna get back to this. So let's define it now. Dynamic equilibrium. When we're at any point along these lines in our phase diagrams, the species are defined to be at equilibrium. And if they're at equilibrium, there won't be net movement of material from one phase into another. Right? If one phase is a lower chemical potential than another, then we can expect the matter to move into the phase of lower chemical potential. But along those curves, we're defining the chemical potentials to be equal. And so what that means is you have no net movement from one phase to the other, but what you do have is an equilibrium movement back and forth between the phases. At equilibrium, say if you have an equilibrium between a liquid and a gas, you will have net movement of liquid molecules into the gas phase, but the rate at which that happens is identical to the rate at which gas phase molecules get trapped into the liquid. And so there's still movement of matter between the two phases. It's just that the rates of exchange are equal and opposite for that. And so you end up with constant composition of the substance at equilibrium. If you move away from equilibrium, you will end up getting net movement into one phase or the other. So if this is a particular equilibrium position for our liquid, and let's say, let's redraw this, let's say we're sitting over here, and there's a plunger, and I've got liquid here, and I've got gas here, and net transfer rates are identical. So I'm at equilibrium. What happens if I pull this plunger back and increase that volume above the surface?
You can have more of the substance going into the gas space.
What's that? Yeah, you can have more of that substance going into the gas phase. Let's try to think of that in terms of our diagram here. I should have labeled this P and T. But if we're at a gas-liquid equilibrium value, and so we're at some point along this line, if we pull that piston back out, what happens to the pressure above the liquid? It decreases. And so if we're sitting at this point, a decrease in pressure moves us down, right? If we're maintaining temperature constant, we're not concerned about changing temperature, so we pull the piston off or pull it out and change the pressure. We move down on the axis, right? And so now we're sitting in a position where the two phases aren't in equilibrium. There's a net favor of the gas phase, right? There's net favoring of the gas phase. So you pull that piston out, your substance is going to start exiting the liquid phase and moving into the gas phase. What's going to happen if you pull that piston out and you just adjust it to a new position and allow the material to sit?
Negative change.
Huh?
There'll be negative change from.
Let's think about this. So one of two things is going to happen. Either you're going to reach a new equilibrium, or you're not going to reach a new equilibrium. So I've got a bunch of liquid sitting down here, right? And I pull this piston out. What's going to happen? Well, first I should describe something. This dynamic equilibrium thing. There's a relationship between the total pressure of the substance in the gas phase and kind of the energetics of the liquid. The liquid's at a specific temperature, and so it's the molecules down here are colliding with the molecules at the surface and popping them out. And the force with which they do that is a function of the temperature of the liquid. How much kinetic energy does the liquid have, right? The higher the temperature, the more force that those guys are going to be popping out with. Where was I going with this? And at equilibrium, you have enough pressure in the gas phase that your gas molecules are colliding fast enough with this surface to be trapped at the same rate that the liquid is leaving the surface. And that was kind of the definition of our equilibrium. Gas is being captured at the same time that liquid is dispersing. But those two rates aren't going to be equal until this pressure is whatever it needs to be in order to have the gas molecules colliding frequently enough to be trapped at the same rate that the liquid molecules leave. And so there's a characteristic pressure that's requisite for this, for that equilibrium. And so you pull this piston out, you increase this volume, gas is going to start moving from the liquid phase, or molecules are going to start moving from the liquid phase into the gas phase. And if there's enough liquid down here, they'll eventually become so many gas molecules that the pressure is equal to what it was back down here, and you'll have a net equilibrium again, right? That might happen. The other thing that might happen is that maybe you didn't have enough liquid down here. Maybe you only had a little bit of liquid, and you pulled that piston out, and all the gas molecules started to try to enter the new volume to reestablish the pressure they had before, but you ran out of fluid. And now all of your stuff is in the gas phase. So one or two things is going to happen. Either you're going to consume liquid and turn it to gas until you reach equilibrium pressure again, or you're not going to have enough liquid and everything's going to drive off into the gas phase. If you have a closed container and there's a substance, solid or liquid, inside that container, there will be a characteristic pressure of the vapor above that container. It's called the vapor pressure of the substance, right? And that vapor pressure changes with temperature. You increase the temperature, you increase the vapor pressure. You decrease the temperature, you decrease the vapor pressure. But you can think of that vapor pressure as being whatever pressure is needed to cause the rate of movement from liquid to gas to be equal to the movement from gas to liquid. It's called the vapor pressure of the substance. We're going to be discussing the vapor pressure substance next week. We'll get into the week after that when we get the chemical potentials. Those will become very important. Okay. So we can do some math. We're going to derive an equation. It's called the Clapeyron Equation. And it asks us to recognize that if we're at a position of equilibrium, if the net movements from one phase to the other are equal and opposite, then the chemical potentials of the two phases must be identical. If the chemical potentials weren't identical, one phase would be favored over the other. And so we know if we have an equilibrium position that we're going to have equal chemical potentials. What we're going to be doing here is we're going to be trying to build an equation that describes for us the positions or the relationships between pressure and temperature along the curves in our phase diagrams. So, assuming that the chemical potentials, the Gibbs free energy of the two phases are equal, we've got the Gibbs free energy of phase 1, which is a function of temperature 1 and pressure 1, is equal to the Gibbs free energy of phase 2, which is a function of temperature 2 and pressure 2. That should be 2. Those should be 2's right there. Sorry about that. G of phase 2 should be a function of temperature 2 and pressure 2. There were the ones on accident. If we move to a new spot, a new value of temperature and pressure, at which the substances are still at equilibrium, so that's basically saying moving, if this is equilibrium position 1, and we're going to move to a new equilibrium position, we might be moving, say, to this point here. And so there'll be a delta T, and a delta P as we move along the equilibrium curve from one point of equilibrium to the other. As we do that, we change temperature and pressure, the Gibbs free energies stay the same because we're remaining on that curve, and so the chemical potentials are equal. And so we can write that the change in the Gibbs free energy of phase 1, moving from point 1 to point 2, is equal to the change in the Gibbs free energy of phase 2, right? Because they're staying in equilibrium, so their chemical potentials must have stayed exactly the same, which means they had to change by the exact same amount. dG, we said last week, was the molar volume times the change in pressure minus the molar entropy times the change in temperature. So we can write the change in the Gibbs free energy of phase 1 as Vm1 dP minus Sm1 dt. And similarly, the change in the Gibbs free energy of the second phase is the volume of that phase times the change in pressure minus the volume of, or minus the entropy of that phase times the change in temperature, right? Kind of reorganizing terms, we get S of phase 2 minus S of phase 1, which is delta S of the phase change, times dt is equal to the molar volume of phase 2 minus the molar volume of phase 1, which is the delta V, the delta change in the molar volume, times dP. We're just going to recast this expression as delta S. We'll stick delta S in over here, and we're going to take delta V and stick it in the denominator, and we get this expression, dP is delta S dt over delta Vm. And if you remember what we talked about last week. Was it last week? Yeah, it was last week. We were talking about the delta S of phase transitions. We said that delta S of any transition, because these phase transitions happen at constant temperature, is just going to be delta H of the transition over T. Do you guys remember that? Does that make sense to you? Because ds was the integral of dq over t, right? But t is constant, and so delta s is the integral of 1 over t times the integral of dq. If it's a constant pressure process, it's the integral of dq is qp, and qp is delta h. Just a quick reminder. And I have to go back to the other notes and remind yourself of that. And so we can replace this delta S for the phase transition with just delta H of the transition over T. And our expression becomes delta H over T times delta T over delta V is equal to delta P. That is known as the Clapeyron Equation, and it describes all of the equilibrium points along these boundaries, the phase boundaries. Okay, for any of these boundaries. You have this is the solid, this is the liquid, and we see the gas. So it might describe the solid liquid boundary, it might describe the liquid gas boundary, it might describe the solid gas boundary. It's equally suited to describing any of those boundaries. What's that? Oh, you're writing it all down? You know I post these, right?
Right.
Okay, fair enough. Do I talk too fast? It's a good thing I have YouTube, huh?
All right, maybe.
So this equation describes the relationships between pressure and temperature along those curves. Let's talk about it for a second. Let's talk about it and let's try to use it to put some logic behind some things that we might have already noticed. If we're looking at one of these curves, let's pick the solid-solid phase boundary for now. Or sorry, the solid-liquid phase boundary. We know that that solid-liquid phase boundary has two different slopes, one for most substances and one for substances that behave like water. Right? And so you got two characteristic kind of phase diagrams. You got most substances and you've got water. And water has that negative slope. In general, if we're talking about fusion, so we're talking about solid going to liquid. What's delta H of fusion going to be?
So
Positive.
this graph, the axis and the is pressure and temperature.
Yep. So if we're talking about fusion and solids going to liquid, what's the sign of delta H here? Does a system have to take energy on or lose energy to go from the solid phase to liquid?
Let's take that.
Has to take energy on. And so if something is gaining energy, we call the delta H positive, right? If it's losing energy, we call it negative. So delta H is positive. Right? What about delta V? What's delta V of fusion for most substances? Does the volume get larger or smaller as you go from solid to liquid? Okay. negative for water. So the slope is just delta P over delta T, right? So how much does P change when T changes by a certain amount? Delta P over delta T is delta H over T times, or divided by delta V, right? If you're talking about most substances for that transition from solid to liquid, delta H is positive, delta V is positive, T is positive, and so we're going to have a positive slope, yeah? And over here, right along that phase boundary between the solid and liquid, we've got a positive slope, yeah? What about water? Water, the delta V is negative. And so if you want to figure out, or so if delta H is positive, the delta V is negative, then the slope's negative. And sure enough, we look over here at water, and we've got a negative slope along that boundary between the solid and liquid. Yeah. Why? You're going to learn all this stuff in your chapter. Why? We noticed that the line between the solid and liquid tends to be larger. The size of the slope, the magnitude of the slope, tends to be larger than the slopes for the solid gas or liquid gas boundaries, respectively. Why? I guess that's kind of a bad question. There's probably several different reasons why, but there's one glaring reason.
You're asking about the magnitude, you said?
Yeah, the magnitudes of the slopes. So slope is delta H over T delta V. What's delta V going to be? How big is delta V going to be for a solid to liquid transition? Not much, because there's not much difference between the volume of the solid and liquid, right? It's a small change. And so because delta V is so small, delta H is going to, not delta H, but the ratio is going to be large. And so you end up with that, boundary between the solid and liquid, you end up having a very large slope, and it's going to be either a positive slope or a negative slope. Along those lines, which of these are all in that line of logic? Why might these two, why would these guys have lower slopes in general? And which one of them should have the largest slope? So these lines describe the solid gas and the liquid gas equilibrium. What's delta V going to be like when you move from a solid to a gas or a liquid to a gas compared to moving from a solid to a solid? It's going to be a lot larger because the gas volume is larger, right? And so your delta V in this equation ends up, delta V of the transition ends up being larger for a solid to gas transition or a liquid to gas transition. And the size of the slope depends on the value of the delta V. You're probably, for most substances, going to get a larger difference between the volume of the solid in the gas than you will the volume of the liquid in the gas, right? Assuming the solid's the smaller volume, then you'll have a larger slope for the solid to gas boundary than you will for the liquid to gas boundary. And both of those slopes will end up being less than the magnitude of the slope of the solid to liquid. Go ahead.
By that same logic, shouldn't the magnitude of the solid to gas be larger than solid to liquid?
Oh wait, did I just say the other one backwards? Okay, so sometimes my brain does the math wrong when I'm doing it fast. Solid to liquid is going to be the smallest delta V, right? And small delta V is going to go to large slope.
Okay.
So solid to gas is going to be the largest delta V. Largest delta V goes to the smallest slope. So I actually drew that backwards. So for that guy, you'd want this guy to have
the gas, right?
the slope like
Okay.
that, yeah? Does that work? If that volume is larger? So I said that absolutely backwards. You guys, thanks for checking my logic. And guess who gets an A? And that's gonna change for water, right? Because water has that different